Hey everyone, and welcome to this explainer. Today, we're diving into the hidden rules that literally govern the infinite and honestly, sometimes totally chaotic world of numbers. We use numbers every single day, right? But just beneath the surface of the ones you're familiar with, there's this entire universe where absolute, predictable order is constantly clashing with endless, non-repeating chaos.
Think about this for a second. How do you accurately measure a number that literally never ends? It's kind of wild to think about. On one side of mathematics, we have these incredibly predictable, highly orderly numbers. But on the other side, we have infinite, wild numbers that seem completely impossible to pin down. So how exactly do we tame that chaos?
Section 1. The Real Number Universe. Let's map out the basics. All right, so within this mathematical universe, our whole foundation is built on what we call rational numbers. By definition, a rational number is basically any number that you can express as a clean, simple fraction. A over b, where both a and b are integers, and b isn't zero. This is the neat, predictable foundation of math where everything just makes perfect logical sense. A nice, clean fraction like 3 over 8. It's clean. It's totally rational.
Okay, let's dive into the complete number system, because it's actually beautifully organized. The real numbers cleanly branch out into two distinct paths. On one side, we have our rational numbers, which further break down into the integers and fractions we just talked about. But then, sitting entirely by themselves on another branch are the irrational numbers. And that branch? That represents the absolute chaos we are going to explore shortly.
Section 2. Rational numbers and decimals. Let's explore how these guys behave.
So, if you take a rational number and actually do the division, it always, and I mean always, does one of two things. For example, 1 over 8 becomes 0.125, and then it just cleanly stops. We call this a terminating decimal. Other fractions don't stop, but they do something highly predictable instead. They loop. 4 over 9 gives us 0.444, just repeating forever. 3 over 7 gives us this neat repeating block of 4, 2, 8, 5, 7, 1. So rational numbers either come to a clean, abrupt stop, or they repeat in a predictable, endless loop. Order and predictability, right? But honestly, here is a brilliant little trick. You don't even have to do the division to know if a fraction will cleanly terminate. There's actually a secret rule hidden right there in the denominator. If you take the bottom number of a fully simplified fraction and break it down into its prime factors, and those factors are strictly 2s or 5s or combination of both, the decimal is guaranteed to terminate neatly. If there's a 3 or a 7 hiding in those factors anywhere, it's gonna loop. It's like a fantastic mathematical cheat code.
Moving on to Section 3, Meet the Irrational Numbers. Time for the rule breakers.
So the crucial point here is the stark contrast between these two worlds. For our rationals, we get those terminating or recurring decimals, but for the irrationals, they are non-terminating and non-recurring. They literally never stop, and they never ever settle into a repeating pattern. They're just a totally unpredictable sequence of digits stretching out into infinity. The square root of 2, the square root of 3, they absolutely cannot be written as a simple fraction, no matter how hard you try.
Let's actually prove how rule-breaking these numbers are. Imagine we assume root 2 equals a over b, fully simplified. If we square both sides, we get 2 equals a squared over b squared. With a little bit of algebra, this means a squared equals 2 times b squared, which makes a an even number. But wait, if a is even, it turns out b must also be even. If they're both even, they share a factor of 2, which entirely contradicts our very first rule that the fraction was fully simplified. Basically, assuming it's rational literally breaks the laws of math. It's a beautiful contradiction.
Section 4. Plotting irrationals visually. How do we trap this chaos?
Now you might be wondering, if the square root of 2 is this wild, infinite decimal, how on earth can we possibly trap it onto a finite number line? Interestingly enough, ancient mathematicians found a genius loophole using geometry. Instead of trying to measure out an endless decimal, they used a Pythagorean theorem to build a physical shape to capture it perfectly.
Let's break down this genius trick step by step. First, you draw a flat baseline exactly 1 unit long on your number line. Then, you go straight up, drawing a perpendicular line exactly 1 unit high. Connect the ends, and you've got a right triangle. According to our friend Pythagoras, 1 squared plus 1 squared equals 2. Therefore, the long side, the hypotenuse, is exactly the square root of 2. So, you take a compass, put the point at 0, stretch it to the top of that triangle, and just draw an arc right down onto your number line. Boom! You have just used geometry to bring absolute precision and order back to a wild, irrational number. Section 5. Taming surds and denominators. Time to clean things up.
First up, we need a quick definition. What exactly is a surd? Well, it's an irrational root of a positive rational number. The square root of 5 is a surd. The cube root of 6 is a surd. But here is a very surprising fact to keep in your back pocket. While all surds are irrational numbers, not all irrational numbers are surds. Take the famous number pi, for example. It's infinitely non-repeating and irrational, but it's not the root of irrational numbers, so it's not a surd. Surds are just their own specific flavor of chaos.
And this brilliantly illustrates what happens when a surd ends up in the denominator of a fraction. It's mathematically super messy. I mean, we really don't like dividing by infinity. To fix this, mathematicians do something called rationalizing the denominator. If we have 1 over the square root of 2, we just multiply the top and bottom by the square root of 2. The chaotic square roots on the bottom multiply together to give us a clean whole number 2. We essentially just move all that chaos up to the top, restoring order on the bottom.
Now, as we look at how all these numbers interact, something totally amazing stands out. If you add or multiply a neat, rational number with a chaotic, irrational number, the chaos always wins. The result is always going to be irrational. However, if you combine two chaotic irrationals together, sometimes they miraculously cure each other. Think about it. If you multiply the square root of 2 by the square root of 2, the irrationals cancel out entirely and you just get 2. A perfectly neat, rational result born directly from two infinite, messy numbers. Which leaves us with this final, provocative thought to take away from our explainer today. Numbers like the square root of 2 or pi are infinitely messy. We can literally never write down their exact final decimal value. Yet these wild, non-repeating, chaotic numbers fundamentally govern the geometry of the physical universe all around us. Every single circle you see, every architectural structure built using triangles, it all relies entirely on the precise interactions of numbers we can never fully write down. Chaos and order aren't just opposites in mathematics. They literally rely on each other to build reality. Thanks so much for joining me today. Keep wondering, and I'll see you next time.